Welcome everyone. So our next speaker is Diego with Snabb, a toolkit for user-space networking.
Hi. Hello, everybody. Hi, thank you very much. Thanks for attending this talk. And this talk title is Snabb. I'm going to talk about this toolkit for programming users' networking functions in user space. It's called Snabb. Basically, what I would like to achieve with this talk is three things: introduce you to Snabb, explain a little bit how it works, and show you what kind of things you can build with Snabb. So let's go for it. What is a Snabb? Snabb is a toolkit for developing network functions in user space, and it's mostly aimed for high-performance networking. And I need to clarify two concepts here in this definition. One is what is a network function, and another one is what is high-performance networking. So a network function is basically a program, any program that manipulates network traffic. These programs, usually what they do is a series of basic operations such as read a packet, forward it, drop it, modify its headers, or create new packets. And combining these primitives, you can build any network function you can think of. For example, a firewall essentially is an application that reads incoming packets, compares them to a table of rules, and executes an action depending on the result. It either forwards the packet or drop it. A network address translator gets incoming packets, modifies its headers, source IP, destination IP, recalculates checksum, and forwards the packet. And a tunneling application gets incoming packets, creates new ones, embeds the old one into the new one, and sends it through the network. So these are the type of applications that you can build with Snabb. And what is about high-performance networking? So the networking field has changed quite a lot in the last 5 or 6 years. What has happened is that the hardware has become much better and the prices have dropped. So nowadays you can get a 10G NIC for 100, 200 bucks, depending on the vendor. So NICs of 25G, 4G are affordable. But still the appliances, the equipment that you find in data centers are still very expensive, these high-end routers by Cisco. So people start to have this idea of maybe I can build a piece of hardware that is equivalent to these high-end routers using commodity off-the-shelf pieces. Maybe you can build a piece of hardware that is equivalent, but you still need to put some software in that hardware. So what would you put? And the natural choice, it feels like it will be Linux, no? Because Linux will conquer the world. We'll put Linux everywhere. But the point is like Linux, it doesn't fit well in this scenario because the way Linux works is a general purpose operating system, and whenever a packet hits the NIC, there's going to be an interrupt, and then the kernel has to handle this packet. It goes through all the networking layer of the kernel until it reaches user space where we are running a network function. So what happens is that a network function is split into LANs, in user space LAN and kernel LAN. And there is a cost of this packet going through the networking layer of the kernel that at these speeds is significant. For example, if we are using a 10G NIC, dealing with packets of 550 bytes, so every 440 nanoseconds, a new packet is hit in the NIC. If we want to process all these packets with one single core at 2.5 gigahertz, that means we have 1,500 cycles per packet for a network function. That's our budget. And this gets worse if the packet is smaller. In the smallest possible packet of 64 byte, we're getting a new packet every 51 nanoseconds. If operations that happen in the kernel, such local locks or an L2 cache miss, has a cost that it will eat almost the whole budget. And there is a great article of a presentation by Jesper Bruet, who is there, hello, where he explains all these things. So people found out this problem in the kernel, and they start to think of solutions. And there are many solutions to this problem. Things in the kernel has improved, also it's worth mentioning that. But one of these solutions was to do a kernel bypass. And a kernel bypass, essentially what it means is you tell the kernel, hey, don't worry about the NIC, leave it to me, I know how to handle, and then you program driver in user space, which is quite hard, no? But that's how you do it. Luke Gorey, the originator of Snabb, and my colleague Kazumo Takikawa delivered a talk about how you can write driver in user space yesterday. And there are other toolkits that follow a similar approach. there's a toolkit very well known called the PDK by Intel. There is a collection of drivers in user space by different vendors. And there is also BPP, now renamed to FDIO by Cisco. It's a project on the Linux Foundation. And it follows a philosophy very similar to Snabb. So let's go with Snabb. Snabb was a project that started in 2012 by Luke Gorey. It's mostly developed in Lua. And Snabb means fast in Swedish. Fast is something that characterizes Snabb because Snabb is fast because it does a kernel bypass. It is fast because it's written in Lua, and network functions are written in Lua, so that's faster than coding in C. It's very easy with Snabb go from idea to code to production. And it's also fast because it runs on top of LuaJIT. LuaJIT is a just-in-time compiler for Lua. It's an extremely fast virtual machine. It's regarded one of the fastest virtual machines out there. And in addition, has very good integration with C, thanks to a foreign function interface that is only available in LuaJIT. It's not implemented by standard Lua. And in Snabb, most of the data types and data structures are actually defined in C. How it works. In Snabb, a network function is essentially a collection of apps connected together via links. And once we have this graph of apps, we pass them to the Snabb engine that is going to run it in units called breadths. So here's an example of a very basic program in Snabb. What we do is like we start the configuration, then we instantiate in this block the apps we need. We need a NIC. This is the driver that's going to read packets from the NIC. And then we have a filtering app that is going to filter packets with source port 80. And then we have a pickup app where we're going to write down packets to an output file. Then on the next block, we connect these apps together. Whatever comes out from the NIC is going to feed the filtering app, and whatever comes out from the filtering app is going to feed the pickup app. We pass down this configuration to the engine, and we run it. This is how it will look like as a graph. Whatever comes out from the NIC, it goes to the filtering app. The filtering app does something with the packets, and whatever comes out is passed to the pickup that eventually writes down the packets to a file. So I said that the Snabb engine processes packets in breadths, and a breadth has two steps. It has an inhale step that is going to put packets, a batch of packets actually, into the graph, and an exhale step, that is going to process those packets. On the inhale step, the method pull of the apps is executed if it's defined, and on the exhale step, the method push of the apps is executed. This is how the pull method of the Intel driver looks like. Well, it leverages on another class called def, but what it does, it loops, and while it can receive packets, it's going to receive a packet and put it in the output link. And this is how the push method of the filtering app we showed before looks like. What it's going to do is going to read the input, the incoming link, and where there are packets, receive them. And if the packet matches the expression, the filtering expression, it's going to transmit it to the output link, and if not, it drops it. As a summary, in Snabb, there are two things to keep in mind, is that usually there's only one app that is going to introduce packets into the graph. I call this app the originator app. This will be apps such as driver that reads packets from the NIC, or for example, a pickup reader that reads packets from a pickup file, or an application that builds packets on the fly. And then all the other apps are going to implement a push method, because the push method is what it gives the apps the opportunity to do something with the packet. This is how a packet looks like in Snabb. It's a very simple data structure. It's an array of bytes, 10K actually, with a length field. And here's how a link looks like. A link is a buffer of packets, 1,000. And it's actually a ring buffer. It has two pointers, a read pointer to read packets from, and a write pointer to write packets to. What kind of things you can do with a Snabb? So you can do anything that has to do with packets, you can build it with a Snabb. But when you start with a Snabb, you don't have to build everything from scratch, because the Snabb already gives you a vast catalog of things that are already built into the toolkit. For example, libraries. You have libraries for parsing protocols, IPv4, IPv6, TCP, calculating checksums. You have apps, drivers, filtering apps, load generators, sockets. I said that Snabb is mostly aimed for high-performance networking, but still you can use the interfaces by the operating system, Unix socket, raw socket, TAP, and it already has full-fledged programs, L2VPN, a Lisper, lightweight after network function, IPFix. On the next slides, I'm going to go through some of these applications that we built, and I will show you what is the things that we did. For example, we built a lightweight after network function. Lightweight after is a network function. It's part of a standard called lightweight 4/6. This is an architecture for deploying IPv6 only networks and still offering IPv4 connectivity and services. It was a project mostly funded by Deutsche Telekom because they are deploying this architecture in their next generation networks called TerraStream. A few months ago, I wrote down a blog post about how lightweight 4/6 actually works. If you are interested, please check it out. Another application we built was Snabb A. It's a L7 firewall, and also does L3 and L4. For the L7 firewalling, we use a library called libntpi. It's an open source library. And for the L3 and L4 filtering, we developed our own domain-specific language called pflang. It was a project funded by LNet Foundation. This is a foundation based in the Netherlands that funds open source project that helps improving the internet. Actually, its chief delivered a talk yesterday, a keynote called The Future of the Internet. And all the information on the development process of Snabb A is at this website, snabb.org. It was a project developed by my colleague Asumu and Adrian. IPFix. IPFix stands for IP Flow Information Export. It's a format for exporting network flows. It's based on Cisco's NetFlow, I think. It was also a project developed by my colleague Asumu. And he wrote down a blog post explaining how the tool was built and how it works. And lastly, this is something that I built recently. It's a DNS service discovery. It's for using Snabb. I developed this as a tutorial to show how you can use Snabb for building programs using TAP interfaces. And what it does, it helps you to discover multicast devices in a local network such as Chromecast or Amazon's Fire TV, etc. And I wrote down a blog post about all the development process from idea to code. So how to get started? All the source code is at GitHub. So you fetch it to GitHub and cd snap make. The community also has around in a Slack channel, slack.com. There's also an official getting started guide, but maybe it's a little bit outdated. A few months ago, I wrote down a blog post called Snabb, explaining it in less than 10 minutes, which is essentially this talk in blog format. And that was all from my side. I hope you like it. And if there are any questions, I'm glad to answer. Thank you very much.
Thank you for the talk, Diego. We do have some time for questions. So.
Thank you for your presentation. I like the idea that Lua is used for programming, and projects that also have a programming capability open with speech. Uses like a low-level not state machine, but like a Turing machine with a set of registers. So have you tried to do some switching, some L2, L3 switches with Snabb?
Okay, I think the question is if we have tried to build a switch with Snabb.
Yeah.
I think you could build it. I think actually there is a learning bridge. That means there is a tool that can learn the mapping between MAC address and a port. But I think, I don't know if it's part of the repository or it was never merged, but there was some attempts to build this tool, a switch.
Hello. Hello, Diego.
Hi.
I read in your GitHub that you have some support for OpenStack. What's the status of this support? So you providing ML2 drivers for OpenStack somehow?
Is it the question that there is support for OpenStack with Snabb?
Yes.
Okay, I'm not very familiar with, but what I know is that Luke Gorey, some years ago, I think it was in 2015, he had to implement Snabb, the interfaces of the neutron layer of OpenStack, so you could plug Snabb into the neutron layer of OpenStack. Does it make sense? Because I'm not very familiar with OpenStack.
Yes.
Yeah,
So
okay.
are you using OVS, Open Virtual Switch, or something like that? Or you are just programming these layer 2 functionalities directly with Snabb?
I don't know. I'm not very familiar. I know that he had to implement that because it was a requirement. It was a long process.
Yeah, OpenStack is like that, yes. So, well, yeah, my last question, sorry. Can you implement using Snabb higher functions like filtering or load balancers or something like that? Thanks.
Okay, load balancers, no. And what was the other one?
Filtering. Firewall.
Firewall. I mean, yes. The question was if we have used Snabb for building high-level applications such as firewall or load balancer. Load balancer, no. And a firewall, the one that I mentioned, Snabbwall, is a firewall even for L7 for application level, and also that's L3 and L4.
So we are out of time now. So if you have any more questions, you can take it off stage, please.
Okay.
Thanks once again.
Thank you very much.